Okay, so let's get right into it. Metal 3D printing. I mean, this stuff is straight out of science fiction. We're talking about building incredibly complex, vital parts for things like jet engines and race cars, literally atom by atom. But, and this is a big but, hidden inside this amazing process is a tiny invisible flaw, an inconsistency so small it can lead to complete catastrophic failure. Today, we're going to crack the code on that flaw.
So think about that for a second. What invisible force could possibly shatter the strongest, most precisely engineered metal? How can something built to withstand unbelievable forces just break? Well, the answer isn't some big dramatic event. It's a quiet chaos, a tiny disruption happening deep inside the machine that messes up everything.
The whole promise of this technology is right here: absolute precision. It's the power to create these wild, intricate shapes that you just couldn't make any other way. You're building solid objects, layer by delicate layer, from a fine metal powder. And that precision, it creates incredible power. We're not talking about trinkets here. We're talking about critical components for the aerospace, automotive, even nuclear industries. These are parts where there is zero, and I mean zero, room for error. But then this happens: failure. A part that looks absolutely perfect on the outside can be hiding a fatal weakness. Just one tiny inconsistency during its birth, and the entire thing can crack under pressure, making it totally useless. And that's the mystery we have to solve. So, to solve this, we've got to figure out where this flaw is even coming from. Our investigation starts at the very heart of the process, with a high-stakes technique that's at the core of all industrial metal printing. It's called Directed Energy Deposition, or DED. The best way to think about it is like a microscopic welding torch that's guided by a computer. A laser melts a tiny pool of metal, and then a stream of metal powder is sprayed right into it, building the part up one delicate layer at a time. Now, for that to work, the flow of that powder has to be perfectly, absolutely consistent. And the difference couldn't be more stark. I mean, look at this. On one side, you have a flawless, powerful component ready to go into a jet engine. On the other, you have a worthless piece of scrap that failed because of some invisible defect. The only thing separating these two is the consistency of that powder flow. So now, we need to zoom in. We're going to the source of the problem, to the very heart of the machine. We're going to look at the mechanism that's responsible for delivering that all-important metal powder. And here it is. This is our prime suspect: the rotary vane feeder, or RVF. Its entire job, its only purpose in life, is to deliver a perfectly steady, predictable stream of powder to that laser. But somewhere in its simple mechanical action, chaos gets introduced. Now, on the surface, this thing looks beautifully simple, right? Powder comes in from the top, a little rotor turns, and a measured amount goes out the bottom. It's kind of like a water wheel, but for dust. But what research found is that underneath this simple action, tiny variations create what's called a perturbation frequency, basically a stutter in the flow. And that stutter leads directly to those hidden catastrophic flaws. So how do you diagnose a problem you can't even see? One that's happening inside a machine with microscopic particles. Well, the researchers brought out a powerful forensic toolkit to expose what's really going on inside that RFE. They basically attacked the problem from 3 different angles. First, they built mathematical models, the blueprint, to try and predict the flow using pure physics. Second, they created a detailed computer simulation, a virtual recreation, to actually watch the chaotic particles move. And finally, they ran real-world physical experiments to get the hard data, the ground truth. Now, even the mathematical blueprint had 2 competing theories. The first, this volume-based approach, is the simple one. It just looks at the size of the feeder's chambers and how fast it's spinning. But the second one, the particle-based approach, is way more complex. It actually models all the forces acting on a single, tiny particle, gravity, air drag, you name it, to try and predict how the whole group will behave. And for that real-world test, they used different kinds of metals, aluminum, iron, and lead, to see how the density of the material would change the flow. They also tweaked the rotor speeds. This super careful work created that essential baseline, the real data that they'd use to judge whether the models were right or wrong. Okay, so the experiments are done. The simulations have been run. The models are ready. This is it. This is the moment of truth. Which one of these tools was finally going to crack the mass flow code and tell us where the chaos was coming from? The first result comes in, And it's for the simple, volume-based model. It lands at only 77% accuracy. A 23% deviation from reality. I mean, it's a decent guess, but for parts that absolutely cannot fail, that's just not good enough. It's clearly missing a big piece of the puzzle. All right, next up, the virtual recreation. The computer simulation, it does way, way better. By modeling how all those little particles actually bump into each other, it hits 92% accuracy. So it's getting much, much closer to what's really happening. But the winner, the model that truly cracked the code, was that more complex mathematical theory. The particle-based approach achieved an incredible 93% accuracy. By focusing on the physics of just one particle, it successfully predicted the behavior of billions. It worked.
And you can really see the difference when you look at it like this: how far each model was from the real world. That volume-based approach is off by a whopping 23% on average. The simulation is much better, at 8%. But the particle-based model is the clear champion, with only a 7% deviation. We found the key.
And here's the answer the model gave us. The chaos isn't just about the speed of the machine. Nope. The most significant factors, the true culprits, are the properties of the powder itself. It's the diameter of each tiny particle and the density of the material. That's what's really controlling the flow. You see, finding this predictive model isn't just some academic victory. This is a breakthrough. It fundamentally changes what's possible in the world of advanced manufacturing. The researchers themselves said it perfectly. Cracking this code is the key to creating truly defect-free parts. By understanding and predicting the flow, manufacturers can now fine-tune everything, not just by messing with the machine, but by choosing the absolute perfect powder for the job. This discovery basically transforms metal 3D printing from a kind of high-tech trial and error into a predictable, reliable science. It opens the door for stronger, lighter, and more complex parts than we've ever been able to make before. So it leaves us with one last really exciting question. Now that we have a blueprint for perfection, what incredible things are we going to build with it?